Okay, everybody, we're getting ready to do lesson chapter 2, review and summary for pre-calculus math today. Email me here for questions, course materials, tutoring. And today, part 1, chapter 2 summary, 0 points here of notebook taking, and you got 80 points here on your classwork sheet. So, teachers, today's bell work is a word problem here about publishing. Top bottom margins 2 inches, each side of 2 inches wide. Draw a diagram that illustrates the problem. And then B, show that the total area A of the page is given by this. So students, give yourself 6 minutes to do this. Teachers, give them 6 minutes. Okay, welcome back for today's solutions for your bell work today. Up here, this will be a fair diagram for this word problem here. 2-inch margins, bottom and top. And you've got 30 square inches of print inside here. And show the total area of the page is given by this expression here. So, x minus 4 times x minus 4 equals 30. And then you, x minus 4, y minus 4, equals 30. Then you solve for y here, and you get this expression here. Then the area would be xy, so that would equal x times, then this will be your y, since you separated that off here, x times that. And then 4x minus 16 plus 30 over x minus 4 when you do your plug-ins here, and then this simplifies to 2x times 2x plus 7 over x minus 4 once you do your simplifying there. So this expression here matches this up here, so that would indeed be an expression which shows your total area of your page. Okay, into our review and summary of Chapter 2, 2.1. We'll find minimum and maximum values of quadratic functions in real-life applications. So consider f of x, ax squared plus bx plus c, with your vertexes here, negative b over 2a. And then you plug this into f to get your y coordinate for that. So a has got to be greater than 0. If a is greater than 0, then f has a minimum at x equals negative b over 2a. And then if a is less than 0, then f has a max at negative b over 2a for x. So let's try a problem here. We have a word problem here. A rectangle is inscribed in a region bounded by the x-axis. So here's your x-axis here, and the y-axis over here. And the graph of x plus 2y minus 8 equals 0, as shown in this figure here. So here's your line there. Write the area A of the rectangle as a function of x, and then determine the domain of the function in the context of the problem. So we have a triangle here, is what we have. And then we have a rectangle here that occupies half the length here. So knowing those two facts there, area equals x times y. So we know that. And if x plus 2y minus 8 equals 0, then y, solving for y, would equal 8 minus x over 2. So that would be this line here when you're solving for that. And then the area would equal x times, so we figured what y was here, 8 minus x over 2. And then the area, when we multiply this out, 4x minus 1/2 x squared here. So that would be your area here, your expression that would express the area of your rectangle here. And then 0 is less than x, and x is less than 8. So knowing that, and then graphing that quadratic, we get this, and then you get a max here. So when you produce a maximum area, Using the graph when x equals 4, the area is a max. When x equals 4, then y equals 2. So that would be the solution to your bell work, students. Or not to bell work, it would be 2.1, I'm sorry. Okay, so for 2.2, using transformations to sketch graphs of polynomial functions, that was what 2.2 was about. The graph of a polynomial function is continuous, no breaks, holes, or gaps, and has only smooth, rounded turns to a polynomial function for a graph. So in this situation here, sketch the graph of y equals x cubed, and then in the graph of the function f. So here is the function here that you need to sketch in to your grid here, and then how that is explain how that is a transformation from y to f is what the question is. So here is y equals x cubed is this one here. Now here you have a negative slope. So, and then you have a vertical translation here of 4. So your y-axis intercept is at 4. And then you have a shift here of, it looks like, between 2 and 3. When you expand this out, you'll figure out that you have a shift here. And also when you plug this into your graphing calculator, you'll see that you'll have this shift here like that. So the graph is a horizontal shift, 1 unit to the right, a reflection in the x-axis, and a vertical shift 3 units upward of y equals x cubed. Okay, 2.3. Use synthetic division to divide polynomials by binomials of the form x minus k. So here is an example here of synthetic division of x plus 3. You change the sign of your divisor, and then you lay out your this polynomial like this here. Drop down, multiply, put up, combine, multiply, combine, multiply, put this here, combine. Then you have a remainder of 1. Okay, so we're going to use synthetic division to divide this by this. Same thing down here for you students in your independent practice, dividing this by this. So when we do that, we have to change the sign of our divisor here. So we go from a negative 2 over 3 to a positive 2 over 3. Drop down, multiply, combine, and then multiply, and then drop down here, combine, negative 27 by 2 over 3, negative 18. So this is a perfect, this is a 0 of this function here. And then down here for 54, x can equal 2 over 3. So this will be your technical answer to this division problem here. So x minus 2 over 3, and then you have 6x cubed minus 27x, and then you have no remainder here is what you would have. And then down here, again, we change the sign of our constant here, and then we drop down, multiply, and then keep multiplying across. And here we do have a remainder of 9 over 4. So your division problem here would be 2x squared plus 3x plus 1/2 plus 9 over 4 over x minus 1/2 for your second independent practice here. Okay, on to 2.4. Use complex conjugates to write the quotient of two complex numbers in standard form. So the complex numbers of the forms a plus bi, a minus bi are complex conjugates to write a plus bi over c plus di in standard form. Multiply by c minus di divided by c minus di, which is 1. So you multiply this by 1, you'll get rid of your complex number in the denominator. You rationalize your denominator. So let's try one of these here. Writing a quotient of complex numbers in standard form. 6 plus I over I, and then down here 1 minus 7I over 2 plus 3I. So this here, we're going to multiply our denominator by negative I to get rid of it, to rationalize our denominator. And then when we do that, we get negative 6I minus I squared over negative I squared, which simplifies to negative 6I plus 1 over 1, which equals 1 minus 6I. And then down here, we're going to multiply this by 2 minus 3I, and FOIL that, and then we get up here in numerator, we get this amount over 4 plus 9, which is 19 over 13 minus 17 over 13I is our complex number for this problem here. 13 in the denominator, and then our real number is 19 over 13, and then our imaginary is over here. Okay, 2.5. Find all zeros of polynomial functions, including complex zeros, and find conjugate pairs of complex zeros. So, complex zeros occur in conjugate pairs. Let f of x be a polynomial function that has real coefficients. If a plus bi is a zero of the function, the conjugate is a minus bi is also a zero of the function. So, up here, to do this one, let's do this one first. The zeros would be 0, and then 2 and 2, this is a square, so you'd have basically a curve that would be tangent at positive 2. You know that just by looking at that. And then down here, you have 4, and then negative 9 here. Again, this will be tangent at negative 9. And then, let's see here, 2.6, find domains and vertical and horizontal asymptotes of rational functions. Domain of a rational function of x includes all real numbers except x values that make the denominator 0. So, knowing that, well, here's our guide practice. Find domain of the function, decide whether the function is continuous, and identify any horizontal and vertical asymptotes. So we have a denominator thus, and then down here, use this, students, as a model to solve your independent practice down here. So the denominator has no real zeros. It would have no real zeros, but it would have imaginary zeros. Domain is all x. Then b, it would be continuous. There's no holes in this. And then the horizontal asymptote would be y equals 2 over 1 would be 2. And then the vertical asymptote, there aren't any vertical asymptotes for that. And then down here, a domain would be all x. It is continuous. Horizontal asymptotes would be y over 3. Again, 3 over 1 would be your horizontal asymptote. And then there is no vertical asymptote here. Okay, on to 2.7. Analyze and sketch graphs of rational functions, including functions with slant asymptotes. So consider a rational function whose denominator is of degree 1 or greater. If the degree of the numerator is exactly 1 more than the degree of the denominator, then the graph of the function has a slant asymptote. So here, these are the same degree here. We're not going to get a shot here to solve a slant asymptote. So go back into your homework, go back into the classwork of 2.7 to find that. Today we're going to find vertical, horizontal, and slants, or any holes in the graph of this function. Then we're going to graph it. So factoring this down, we get this here, and then these two would cancel. We get x minus 4 over x plus 1. Vertical asymptote will be x equals negative 1. Horizontal asymptote will be y equals 1. They both have the same here, so it'll be 1 over 1 would be your horizontal asymptote. No slant asymptotes. And then we got a hole at x equals 1 for here. And then into 2.8. 2.8, classify scatter plots, find quadratic models for data, and choose a model that best fits a set of data. So sometimes it's not easy to distinguish from a scatter plot which type of model best fits the data. You should first find several models for the data and then choose the model that best fits the data by comparing y values of each model with the actual y values. So in this one here, we need to, well, that does definitely looks like a quadratic, and this looks like neither, so that's kind of a softball. And that was your review of summary for Chapter 2 of Pre-Calculus Math. If you need any lessons or homework or note-taking guides, or if you need to get a hold of a PowerPoint or video from Chapter 2, email me here and I can get those out to you. Thank you very much.